Good morning, everybody, and welcome back to Next Door NetAdmin. Today, I thought that I would do something a little different. Rather than talking solely about current items, I thought we would go and take a stroll through history lane, as it were. This comes out of last week's video where I was talking about the OSI model and all the various layers that we went through. And I realized that there's a lot of terminology that network engineers and admins kind of just throw around because we know what it means. But if you're starting out, you may not know how this term became a thing, what it means, what the context is in terms of what it means to everybody who's been around with it for quite a while. So that's why I thought I'd just go through this and cover some of our older technologies. They may not be currently useful, they may not be in use anywhere, and some of them I dearly hope they are not, because we have stuff that's so much better now. But if we go through that, then hopefully it gives you more insight into the equipment that we talk about, the terms that are in use, and it can enhance your knowledge and understanding of what you're working with, even in a modern context. Cool. So, what we're going to be talking about today is mostly at layers 1 and layers 2. That was the physical layer and the data link layer. The physical layer, all we're going to be talking about is cabled. We're not going to be talking about radio today because that's its own thing completely. And layer 2, while we're going to talk about layer 2 kind of in abstract, most of what I'm going to be talking about will be Ethernet based. But did you know Ethernet didn't just used to be the cables that we work with today, what you would call twisted pair? Ethernet as a standard started out with coax cables. There was thicknet and thinnet, mainly having to do with, how thick the cable was. Thicknet had more shielding, and so it could run for a further length. And thinnet was thinner, easier to work with, but because it had less shielding, it had greater attenuation, and the signal would not travel as far. This was important because both thinnet and thicknet with the coax cables ran as a single bus. This is something that I mentioned last week as well. It used to be a bus architecture and still is fundamentally. But you would literally have a cable that ran from one end of your network run all the way to the other. That was the network run. And then each computer would have essentially a BNC connector that would connect to a T-shaped tap that would tap into the line. Remember that word, it'll come back later. But when every computer has a tap into the same bus, again, how does this work? How does your traffic signaling work? Well, something that we mentioned last week was CSMA CD, and I said it wrong in the video, but if you read the description, you'll know I caught my error afterwards. Whoopsie. But collision, no, that's wrong. Carrier sense multiple access with collision detection. There we go. Carrier sense, there's a wire there. Yeah, okay. Multiple access, there's multiple computers tapped into this line. We got that too. Collision detection is the important thing. When a station transmits onto the line, before it transmits, it's going to listen first to see if any other station is transmitting on the medium. But there's always the risk that two stations try to transmit at the same time. When that happens, they detect that a collision has occurred. I'm still transmitting and I can hear that somebody else has just started transmitting too. And when that happens, there's been a collision on the network. This is important because early Ethernet was also half duplex. Half duplex essentially means that you can only transmit or receive. You can't do both at the same time. And so this is a little bit like walkie-talkies. If you've ever had one walkie-talkie and you talk into it, that's great. Everybody else can hear you. If you try to key up two walkie-talkies on the same frequency, what do you get? You get an awful, awful squeal because there's two stations broadcasting at the same time and everybody else is receiving both, and it just washes it all out into an awful, awful squeal. Something similar happens on a bus architecture, a half duplex bus architecture for computers. And so if they detect that a collision has occurred, they know that nobody else can understand what's happened. And so both stations, when they detect a collision, will emit a jamming signal. A jamming signal just to indicate this has failed, and both of them broadcast so that they can both detect that the jamming signal is being broadcast and therefore a collision has occurred. Okay. That's cool. All right, so we've got ThinNet or ThickNet. It is a single bus. It is half duplex, and everybody has a tap onto the same bus line. Okay, cool. This is where it starts. What happens if you want to extend your network? Both of these have length limitations. So what do? Well, the simplest thing you can do at layer 1 is, what was the length limitation in the first place? The signal got too weak. Well, if you can just increase the strength of the signal, then you can keep the network path going. And that's where we get a repeater. Very basic. If you've used ham radio at all, amateur radio, then you're probably already familiar with the concept of a repeater. A network repeater works in much the same fashion. It hears a signal, it increases the signal strength, and rebroadcasts it. Crucially, though, like I said, this is at layer 1. The repeater does not need to understand anything about Ethernet. It doesn't have to understand anything about IP. It doesn't have to understand anything about HTTP, Telnet, port numbers, any of that junk. It just worries about, I'm receiving a signal, I'm putting it out the other end at a stronger signal strength. That's it. You can do the same thing with fiber optics, incidentally. You can get optical repeaters that increase the light strength and rebroadcast that. And that is something that is necessary, for example, in transatlantic cables, because it's a long distance and the light won't come out the other end at nearly the same strength as it went in. So you need optical repeaters. But the repeater is just an extender. No more, no less. Okay. There's still a maximum distance that you can run with this. And the maximum distance total comes down to how long does it take at the minimum frame size for Ethernet. If a station at one end of the line starts transmitting and a station at the other end of the line starts transmitting at the same time, they both need to detect it before they've reached the end of their minimum frame size so that they can emit the jamming signal if they both transmit it at the same time. So if you calculate this out at essentially the speed of light, the speed of electricity transmission, you get a maximum length that you can actually run your network, even with repeaters in play. And this forms what we call a collision domain. A collision domain is a segment where any collision can be detected and reported correctly. Okay, cool. So, you have repeaters. You have a long, coax cable. All right. Well, then we increased our understanding of technology and developed twisted pair cabling, which is what we're still using now. There's a couple of different variants, by the way. You can have shielded twisted pair, foil shielded twisted pair, unshielded twisted pair, or UTP is the standard that is commonly used. So, cool. But with a twisted pair cable, we moved from a single bus architecture to a star topology, where we have a bunch of cables going to endpoints and they all converge at a central point. Or an extended star topology, where you have multiple, concentration points, and those concentration points are linked. A repeater only has one in and one out, so this isn't going to be useful. In a star topology enabled by twisted pair cabling, you now need a multi-port repeater, which also became known as a hub. Hubs also work on layer 1. It's accept a signal in one port, broadcast it out all the others at increased signal strength, and you're done. That's it. So that's cool. We can now connect more machines without having to tap a single physical line that has to snake through all the desks back and forth. That's cool. But would it kind of be cool if we could extend the length of the network, which has a fixed size because we have a maximum size of our collision domain? Would it be kind of cool if we could have kind of two networks? Two different collision domains? How do we join that? Well, we can bridge them. And so a new device is born, the bridge. The bridge works on layer 2. Why does it work on layer 2? Well, because it's separating collision domains. Collision domains are a function of Ethernet, which means that it is a layer 2 concept. And so if you're going to bridge two different collision domains, you're operating at layer 2. A bridge is very simple. It listens to traffic going through on one side, and when it hears somebody transmitting something for a station that's on the other network, it passes it over. And if it doesn't have to pass it over, it doesn't. The rest is just a bus architecture on either side. They can just keep talking to each other. Only the traffic that has to be bridged will flow over the bridge. Cool. Can this bridge two different layer 2 technologies? Yes, it absolutely can. There is nothing to say that you couldn't use an IP address that you're talking to somebody else, because that's at layer 3. You could be on Ethernet. The other station might be on token ring. It might be on frame relay. You don't need to know that. All you need to know is a consistent way of addressing it with a TCP port at layer 4, an IP address at layer 3. Layer 2 is determined by your local network because it's got a maximum size that you can practically run. So you might have a bridge that is listening to Ethernet traffic going back and forth. And when it hears something that kind of needs to go over to the frame relay side, it will bridge those two different networks and broadcast it out onto the frame relay side. That is something that you can do. It's kind of cool when you think about it. Most of the time you won't, because most networks are Ethernet these days. It's just how it is. Okay, so you've still got two big collision domains here. If we're talking about, half duplex, you can also get full duplex, where your equipment knows that you can transmit and receive at the same time. If you can transmit and receive at the same time, that's a full duplex connection. And it speeds things up dramatically because people can send and receive at the same time. But on a bus architecture, only one station can be transmitting at a time, even if it can receive at the same. Well, I take that back. Only one pair of stations can be transmitting and receiving at the same time, is what I want to say. When you came to full duplex communication, and cool, what happens if you're talking to a station that doesn't understand full duplex? Well, if you're using auto configuration, it's going to default back to the lowest common denominator, which is a half duplex connection. So you've still got, even if you are technically full duplex capable, if auto configuration doesn't work, or if you have a device that just doesn't understand full duplex, you're still going to fall back to half duplex. Okay. So you've got these two collision domains where you might have half duplex connections, you might have full duplex connections, we don't know. And when it needs to cross between collision domains, it'll flow through the bridge. What if we could shrink the collision domains even further? This is how we get to a switch. A switch fundamentally works in much the same way as a bridge does. It accepts traffic in one port, but then it's fully segmented. You're not going through any hubs or repeaters along the way. The switch kind of takes the place of all of these. And it will, if it doesn't know where the destination is on which port, it has to send it out all of those ports because it doesn't know where the destination station is. But if it does know where the destination station is located, then just like a bridge, it will only send it out the destination network side. This means that you can have two stations talking back and forth with each other, and none of the rest of the network has to see it, which means you've dropped the size of your collision domains dramatically because the switch also operates on layer 2. And even better than that, because the switch is sitting in the middle between these two stations, typically speaking, your collision domain is actually just the single wire segment, because the end station is talking to the switch, and then the switch talks back to the station by relaying the traffic. And so at layer 2, your collision domain has basically dropped to a single wire. And you won't have collisions anymore unless you happen to be operating in half duplex for some reason. And if you are, then you probably have a problem that you need to fix. Gigabit. Gigabit kicked this up by a lot. Twisted pair cabling has 4 pairs of cabling, 2 wires each. Okay, cool. Both 10 megabit and 100 megabit used 1 pair for transmission and 1 pair for receiving, transmitting, receiving. And then the other 2 pair were ground. And it was actually designed this way so that you had phone lines essentially had 2 ground and 2 data. That was it. So 4 wires in a phone cable, you could actually rig up your Ethernet or 4 pair 8-wire cable, so that you could plug a phone line into the middle of it and it would work. You could just transmit a phone line over that. And then the other 2 on the sides could be used to create another phone line if you wanted, or in the case of Ethernet, you'd have a couple of unused pairs that could be used for ground, providing power, etc. Gigabit was enabled by essentially advanced electronics that could make better sense out of what was happening on the wire, electrically speaking. Because with gigabit, you're using all 4 pairs in both directions at the same time. With gigabit, each pair of wires is carrying 250 megabits of traffic at the same time, full duplex, both directions at the same time. So the electronics has to be good enough to separate its own signal out from what is being received and understand how those 2 different electrical waveforms will balance each other and cancel each other out, or just increase each other to dramatic levels. It has to be continuously error correcting in order to make heads or tails out of what the other side is sending. So this was not something that could be done on, at least certainly not off the get-go. It took quite a bit more development to get to that point. But all of this that I've talked about has happened at layer 2 or layer 1. And I mentioned way back a ways that in the original bus architecture, each station would have a tap into the main bus line. That terminology is still used today. If you look at some of the, I want to say OpenVPN definitely uses this terminology. I think Linux uses it sometimes as well. But you can see concepts like a bridge. You can also see in OpenVPN, I'm going to use it because it's the perfect example for this. One of the available interface methods is tap. And when you're using a tap interface, you are running at layer 2. So that any layer 2 traffic coming in one side will get sent through and emitted onto the layer 2 network at the other side. That is a tap interface. You've created a virtual tap into your bus on the other side. So the terminology still exists. The concepts are still useful, even if we've moved past that architecture to more modern forms. It's cool. I do plan on continuing with this discussion, and we'll see about how, routers function in more detail. The last thing I will leave you with, though, is a caution. Because the terminology that I have explained here, the device names and everything, are what we commonly understand it to be. There are some companies that decide to redefine what it means for their own benefit. Kind of like how Tesla tells you that it's full self-driving, and it's not. They've redefined it by sticking a trademark symbol on the end of it, capitalizing every word, and say, oh, well, we don't mean that it's full self-driving. It's full self-driving. So, one of the networking appliances I've worked with before is Untangle. And this is what I'm familiar with, so I'm going to use it as an example. But I have no doubt that this happens with other filtering appliances as well. One of the modes that Untangle offered was a transparent bridge mode. If it's a bridge, you expect that what you send in one side will flow to the other if necessary on layer 2. and it doesn't care about the layer 3 whatsoever. You could be using IP, you could be using IPX, SPX, you could be using something completely different. It doesn't matter. It's a bridge. It's only operating on layer 2. But that's not how Untangle's bridge mode works. And it's something that they had to put into their documentation, and it would continually trip up newbies, myself included, at least until I understood this, that the way that the filtering worked is it would accept packets or frames in one side, destroy them, pass the traffic up through the filtering appliance, and then it would come back down on the other side, and it would recreate the whole thing and send it out the other side. That's not operating at layer 2. And in fact, it can't in order to make that architecture work. But the key point to this was where a bridge does not care about your layer 3 addressing, Untangle very much does, because it's going up through the whole layer stack and coming down the other side. Because of this, it had to be emphasized, even in bridge mode, everything this does is routed. It's operating on layer 3 because it has to. Even though we've used the term bridge because that's kind of what it looks like to people who don't know any better, it's not actually functioning as a bridge. And if you slapped it down and gave it to a network engineer who doesn't know anything about how it's working and say, this is in bridge mode, you expect it to just pass traffic through, and you don't need to tell it where all of your layer 3 networks are. If you do that, it doesn't work. So just be cautious. Even if you understand what the word means, what it's supposed to mean, the equipment that it came from, that doesn't mean that everybody's going to use it the same way. You got to watch out for that kind of spontaneous redefinition, shall we say. But, like I said, I plan to talk more about this in future, talk more about layer 3 and higher levels, because you can get into lots of other details. For now, though, I think that's probably enough to chew on for 1 week, and next week is the freeform, so we'll probably pick this up in 2 weeks from now. Okay. Well, that's it for today then. Thank you very much for watching. I am your Next Door NetAdmin, and we'll see you next time.